Okay, hello everyone. Our discussion for today is on math foundation, but before we discuss, we move on to our learning outcomes for this chapter. We have the first one is to distinguish the difference between combined foundation and math foundation. 2, to identify the use of math foundation. 3, apply the design considerations of math foundation. And 4, compute math foundation related problems. Of course, it is being stated that under normal conditions, the square footing and rectangular footing are the most economical for supporting columns and walls. However, under certain circumstances, it may be desirable to construct a footing that supports a line of 2 or more columns. So that is what we call combined footing. So meaning to say, there are specific situation wherein a combined footing is desirable to be constructed which can support a line of 2 or more columns. So for combined footing can be classified as rectangular footing, trapezoidal footing, and strap footing. So, however, when more than one line of columns is supported by a concrete slab, it is called a mat foundation. So, basically, mat foundation are generally used with soil which has a low bearing capacity. So before we move on to mat foundation, let us identify some of the consideration for the analysis of combined footing. So we have here a rectangular combined footing. So for rectangular combined footing, if you're going to identify the net allowable soil pressure, so with a size of a foundation which is B times L, so we can have this steps in our to analyze rectangular combined footing. Of course, you have here a combined footing, you have a width B, and of course the length is L, and this is having a two column in one. The column is along a one line. So we have Q1 and Q2 refers to the column load. So if you're going to, the first step is to determine the area of the foundation. So that is A is equal to Q1 plus Q2 all over the net allowable soil bearing capacity. And we have to determine the location of the resultant of the columns. So basically for this, if you're going to observe, we are trying in this chapter, we are on the review of what we learned in our statics and strength of materials. So we are going to identify the resultant of the column loads. So actually this is resultant force, total resultant, or the resultant force times X equal to Q1 times L1 plus Q2 times L sub 2. So for this one, we simply have to specify that the location of the resultant of the column loads is capital X equal to Q sub 2 times L sub 3 all over Q1 plus Q sub 2. So for letter C, the third one, if for a uniform distribution of soil pressure under the foundation, the resultant of the column load should pass through the centroid of the foundation. So if there is a uniform distribution of the soil pressure under the foundation, so our resultant column load, it should pass through the centroid of the foundation, and the length of the foundation now is equal to 2 times L sub 2 plus capital X, which is our location of the resultant of the column loads. And the fourth one, once the length L is determined, you have to find the value of L1 and can be obtained as follows. So for this one, you have L1 is equal to L minus L2 minus L sub 3. So you have to take note that the magnitude of L2 can be known and depends on the location of the property line. So the fifth one, you have to determine the width of the foundation, which is B is equal to area all over the length. And we have what we call the trapezoidal combined footing. So for the trapezoidal combined footing, So basically for this, this is being used when the column are used to carry unequal loads when the distance outside the column of the heaviest load is limited. So if there is an equal distribution of load, it is advisable to use a trapezoidal combined footing. So for this one, you have here an illustration for a trapezoidal combined footing. Of course, you have different width. You have B1 and B sub 2. You still have the column load, Q1 and Q2, and this is our resultant force. This is the location of the resultant force. This would be our reference line, so that we can identify our location of the resultant force. Same procedure, you have to identify the allowable soil pressure. So if you are going to identify the area of the foundation, so you have area is equal to Q1 plus Q2 all over net allowable soil bearing capacity. And from this figure, you can have the equation that the area of the foundation is equal to B1 plus B2 all over 2 times L. And to locate the location, to find the location of the resultant force, you have here, you have similar equation from our rectangular combined footing. So from the property of the trapezoid, you can have this equation that x plus L sub 2 is equal to quantity B1 plus 2 B sub 2 all over B1 plus B sub 2 times L all over 3. So you have to take note that with known values of A, L, and X, and L sub 2, so to obtain B1 and B2, you have to take note for this trapezoid that X plus L sub 2, which should be greater than L all over 3 but less than L over 2. For cantilever footing, you have a construction of a strap beam to connect an eccentrically loaded column foundation to a foundation with an interior column. So this is an illustration of a cantilever footing. It uses a strap beam. So for this one, the purpose of the cantilever footing is to redistribute excess stresses and possible differential settlement between adjacent spread footing. So if you're going to observe, we have here two columns. It is being connected by a strap beam. So we move on now to mat foundation. So basically, mat foundation, as mentioned a while ago, it is also known as raft foundation. So it is essentially a continuous slab resting on the soil that extends over the entire footprint of a building, thereby supporting the building and transferring its weight to the ground. So for this one, for a mat foundation, which is also known as raft foundation, is a combined footing that may cover the entire area under structure supporting several columns and walls. So mat foundation are sometimes preferred for soil that have a low bearing capacity but that will help to support high column or wall loads. So basically, for mat foundation, this is being used if the soil has a low bearing capacity and it will support high column or wall loads. So pag matataas, big structures that is constructed on low bearing capacity, it is advisable to use a mat foundation. So basically, the mat foundation or rough foundation is also very good for basement. So it is also good for basement construction. Foundations are created by excavating soil in order to find strong, compact, and distributed natural soil that is at least a few feet below ground level. So this soil is much stronger than the loose soil at the surface. So if we construct a rough foundation, for example, that is 10 feet below the ground, and build concrete walls around the periphery, this makes an excellent building, basement rather. So therefore, an engineer would design a building with a basement that will tend to choose a rough foundation over other types of foundation. So we have here the different common types of mat foundation. So we have a flat plate. This is a flat plate. This is the flat plate. You have a flat plate thickened under columns. So you have a flat plate, then we have a thick under columns. Then we have a beam and slab. The beam run both ways and the column are on the intersection. The column are on the intersection of the beams. So we have this an illustration for letter C. Then the fourth one is a flat plate with pedestal. So this is a flat plate with pedestal. This is a slab with basement. So this is the fifth one. So those are common types of mat foundation. So we have here an illustration, the difference between the depth and the width of the isolated foundations and mat foundation. So this is an isolated foundation and this is a mat foundation. So there is a difference between df and our width of the foundation. So this is for isolated foundation, this is our df and this is our base or the width of the foundation. For mat foundation, this is df and this is the width of the foundation. So the comparison between isolated foundation and the mat foundation in terms of their depth and their width. So to compute the bearing, of course, for mat foundation, we are trying to compute the bearing capacity for mat foundation. So basically, for the computation to find the bearing capacity of mat foundation, you are going to make use of this formula. Of course, you know that this formula is the formula of Mayer-Off. So to compute for the mat foundation bearing capacity, you're going to make use of the Mayer-Off formula. And this is the gross ultimate bearing capacity. Gross ultimate bearing capacity. So this is the Mayer-Off equation. So if you're going to compute the net ultimate capacity of a mat foundation, of course, you simply have to subtract your effective surcharge from the gross ultimate bearing capacity. So for the factor of safety, the factor of safety should not be less than 3 under the dead load or maximum live load for mats constructed on clay type soil. However, under the most extreme condition, the factor of safety should be at least 1.75 to 2. So for mat foundation constructed over sand, a factor of safety of 3 should normally be used or be utilized. Under most working conditions, the factor of safety against bearing capacity failure of mats on sand is very large. So for this one, you are going to make use of the factor of safety, which is 3 for a mat that is constructed on clay. However, for extreme condition, you're going to use 1.75 to 2. And for a mat that is constructed over sand, you're going to use the factor of safety, which is 3. So this is the condition for mats that are mat foundation constructed over sand. So the factor of safety against bearing capacity failure of mat on sand is very large. So this is the ultimate bearing capacity for our mat foundation. So you have to take note that Cu is our undrained condition, and N sub C is 5.14, and N sub Q is 1, and N sub gamma is 0. And for our sum of the shape and depth factors, you have now the equation. And because of this shape and depth factors, our equation for the ultimate bearing capacity can be simplified into this equation. Of course, this is plus Q, which is our effective surcharge.